Hello class, and welcome to section 1.6, inverse functions. There is a part A as well as a part B, and we will be covering both A and B in this particular YouTube video. In our warm-up here, we can see it says perform the following transformation on each set or each ordered pair in the given function. Write your result as a set of ordered pairs. Okay, so in our warm-up, we can see here x comma y to y comma x, which is a precursor to the following, what we call the inverse f of x, or f inverse of x. In terms of the xy table that we see, we've got 1, 2, 3, 4, and 5, and then 4, 3, 2, 1, 0. So if we were to quite literally just flip the x and the y coordinate so that it's y comma x, we'll write this as x, but now f inverse of x. 4, 3, 2, 1, 0. And then 1, 2, 3, 4, and 5. So the set that we can go ahead and identify with, flipping the x's and the y's, 4 comma 1, 3, 2, 2, 3, 1, 4, and 0, 5. Which takes us to a concept that is not brand new, and that is the inverse function, or inverse functions. And I say not brand new, we did, and you did see this in Algebra 2. Let's go ahead and take a look at it again. A new function that returns each output of the original function to its input. An inverse function is denoted as follows. The inverse of f of x is denoted by f, and it looks like a negative 1 exponent. It's not. It's just the inverse of f of x, or f inverse of x. So in our first example, we're going to go ahead and find the inverse of the function f of x equals x plus 7 informally. And simply what that means is we'll create an xy table, first for x f of x, and then we'll create one for x and f inverse of x. Now because this is a function of linear nature, we really only need 2 points to get a grasp of maybe then the graph of this particular function. But maybe we'll go ahead and use more than 2 points just for the sake of adding more to our list and seeing more. So 0, 1, and 2, and 0, 1, and 2. So I'm already preparing you to use pretty simplistic x's for the original function, but also flipping the x's and the y's, not knowing quite yet what I'll have for the input, because the input here will be the same as the output there. We'll go ahead and prepare ourselves so that, yes, when we do plug in 0, 0 plus 7, 1 plus 7, 2 plus 7, those outputs are the inputs of the inverse. So let's go ahead and find the inverse more formally. It is a two-step process. First step, rewrite the function in terms of y instead of f of x. We want to switch x and y, which we've obviously done in that particular setup, and then simply just get y by itself. Subtract 7, and this is the inverse. Now, if it makes sense to then plug in 7 into f inverse of x, 7 minus 7 better be 0, and it is. 8, 8 minus 7, 1, and 9, 9 minus 7, 2. So this is, in fact, the inverse formally. Let's continue. On this next example, again, we see a linear function. I'll do the same process here, setting up an x f of x table, and then, of course, an x f inverse of x table, f inverse x table. I'll pick numbers 0, 1, and 2, knowing in advance again that the inputs of one will be the outputs of the other, so I'll just switch Then we'll do the math. 2 times 0, 2 times 1, 2 times 2. Those particular outputs are now the inputs of f inverse of x, and there you have it. The informal approach, again, I'll say y equals, in this case, 2x. Switch x and y, and then solve for y. Divide by 2 or multiply by 1/2, and that is your inverse. If I were to again plug in the x that I came up with, 0, 2, and 4, plug it in here, 1/2 times 0 is 0, 1/2 times 2 plugged in here is 1, 1/2 times 4 is in fact 2. Moving on. So here's our formal definition of the inverse. Let f and g be two functions such that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. I want you to circle x in both instances. Formally, when we do verify inverses, and that's a very, very important word that I'm going to highlight. I'm going to write verify here. The word verify does demand that we do two different compositions, f of g and g of f. Under these conditions, the function g is the inverse of the function f. Function g is denoted as f inverse, and we'll read it as such. So f of f inverse equals x, and f inverse of f equals x. The domain of f must be equal to the range of f inverse, and the range of f must be equal to the domain of f inverse. As I said, the inputs of one become the outputs of the other, and vice versa. So let's apply the definition. And be very, very careful, as it says, applying the definition to verify that two functions are inverses. So verify. We have f of x equals 3x cubed plus 1, and g of x equals the cube root of x minus 1 all over 3. So we must, in verifying, we must do f of g of x, which hopefully is equal to x. If they're inverses, they will. And of course, g of f of x also must be equal to x. It is crucial, I can't stress enough, that we understand the difference between verifying versus finding. We are not actually finding the inverse, we are verifying that they are, in fact, inverses. So as we hopefully recall from previous sections, we can do the composition simply by taking the g, which is the cube root of x minus 1 over 3, and that is my g function. I will be substituting now that into the f for x. The x that you see in terms of the f of x is here, and that's 3x cubed plus 1. So I'll use kind of a larger set of parentheses, substituting in the expression cube root of x minus 1 over 3, and that quantity is cubed, because again it's 3x cubed, and that's plus 1. The way that I like to break this down, I will be able to show on either side here, both f of g and g of f, hopefully that they're both equal to x. So if I go ahead and continue, I'll go ahead and cube this cube root. So this becomes 3. The cube root of something cubed is just that something, and the quantity, in this case, x minus 1 over 3. It's the radicand, essentially. Still plus 1. And we'll continue. As you can hopefully see, we can take 3 divided by 3. So what we're left with is x minus 1 plus 1, which then leaves us, as those two cancel, simply with x. I like to put a little check mark here, identifying with the fact that we are done with that half of the problem. Now it's time to move on to g of f. Again, remembering that the f function was 3x cubed plus 1. My goal, yet again, is to substitute 3x cubed plus 1, that particular expression, substitute, into the g function now. The g function was cube root, and it was x minus 1, so the quantity x I'm going to now write is 3x cubed plus 1, and then that's minus 1 all over 3. Again, this entire quantity is the substitute for x into the g function. Now we go ahead and simplify. Now, I could get rid of the parentheses in the previous step, but I think I'll do that now. In this step, wherein these are going to subtract. And in the next step, and only in the next step, can I see then that the 3's will divide out, which leaves me with the following. Cube root of x cubed. Well, as it turns out, the cube root of x cubed is simply x. And lo and behold, I have in fact verified that that half is x. So yes, these are in fact inverses. Moving on. We're continuing into 1.6b, and traditionally, based upon time, this particular section, or at least part of the section, may have been carried over into the next day. But with our time, things are moving along very nicely, and I think we can move ahead here. The graph of an inverse. So to obtain the graph of an inverse function, we reflect the original graph over the line y equals x. Let's highlight this. So y equals x, I like to deem it as the quote-unquote line of symmetry or axis of symmetry. It's my informal definition, or I guess you could say just approach to dealing with inverses. Put quotes around axis of symmetry. For no other reason than that's my way of saying it. But it helps to think about it that way, because what we're about to do, as you can see in the example, given the graph of g of x, sketch the graph of g inverse of x. What we're about to do is take every single point on the g function, and I'm going to go ahead and just plot just a couple here to highlight where I'm going to go with this. Pick a point, let's say here, just some arbitrary intercepts might help. I guess this point here, maybe another point here. It's kind of like almost like a max, so to speak, of the g function. And what we're going to go ahead and do is think about taking each one of those respective points and reflecting them about that quote-unquote axis of symmetry line. Now, one of the things that might help in determining where I'm going to put the inverse function thanks to that axis of symmetry is think about taking the x and the y, of course, and switching them. Okay? So this particular point, I guess we'll start here. This is on the x-axis. Let's pretend for a moment it's 4, 0. If I take 4, 0 and flip the 2 so it becomes 0, 4, it lands somewhere here roughly. Similarly, if this point down here is 0, -3, if I flip, it becomes -3, 0. This point is on the axis of symmetry, so it doesn't go anywhere. And then lastly, this point appears to be roughly -5 or 6, -1. Let's say -6, -1. Flip that, becomes -1, -6. So it's somewhere here, roughly. In terms of connecting the points, so you have a smooth curve, it should be relatively nice in that you'll have a continuous curve as such. So that is your inverse, and we'll label it as such. We'll call that g inverse, or inverse of g of x. Moving on. As a follow-up, it does say, or ask, is the inverse actually a function? Well, that's where the vertical line test comes about again. Vertical line test, or VLT. So if you recall, we want to ask ourselves, anytime we look at a relation, in terms of then, of course, defining it as a function, we want to see if it passes the vertical line test. Does this pass the vertical line test? Let's see. It looks like it fails. So because it fails the vertical line test, the conclusion is that the inverse is not